Welcome, ladies and gentlemen. Let's go ahead and get started with our discussion today. We need to be able to use Riemann sums. That's just a fancy way for saying use rectangles to find an approximation for the area underneath the curve. So I think of a Riemann sum as a rectangle, and then we'll be told different ways in which to gain the heights of those rectangles. And so let's consider our first question. Here we're going to use 4 rectangles in order to approximate the upper Riemann sum on the x interval 1 to 3. And so for this one, we're doing an upper approximation. And upper means that we're going to take the greatest function value. And so, Paige, when I was talking about you before, I thought we were doing midpoint. Instead, we're doing an upper Riemann sum. That means that we want to go ahead and use the greatest function value that occurs over the course of each subinterval and use that to generate the height of the rectangle on that subinterval. So just as, okay, we did say that each time. All right, so we're okay. So let's go ahead and figure out what this is going to look like. Again, we'll take our entire width of our interval, that is 1 to 3, and we'll divide it into the number of rectangles. Here we're going to partition our overall interval into 4 equal subintervals. And so to get my delta x, we'll use our calculation b minus a all over n. For us, that's the n.3 minus 1 all over 4, and it looks to me like delta x then is going to be 1/2. So it looks to me like each rectangle is going to have a width of 1/2 units. So let's go ahead and draw those in. So we'll go ahead and starting at 1, and we'll have snap. And we need 4 rectangles, so it looks like right here too. Okay, so we'll partition our interval into 4 equal subintervals, each with delta x, and then we need the height of those rectangles. Where do we go to get the height? That depends on the directions. Sometimes we'll look at the midpoint of each subinterval to get the height of the rectangle. Sometimes we'll look at the left-hand side. Sometimes we'll look at the right-hand side. In this case, we're looking at the upper. Upper doesn't mean right-hand side or left-hand side, necessarily. It means the greatest function value attained over each subinterval. So as I look at this first subinterval, it appears as though the height of my rectangle will be gained by looking at the greatest function value. In this case, it is the right-hand side. So in this case, it is the right-hand side. That will determine the height of that first rectangle. Oh my, that's not going to work very well. And then the right-hand side again, and the right-hand side again, and the right-hand side again. And that is as a result of asking for an upper. It's not always the right-hand side. It could be the left-hand side. We're just taking the greatest function value that occurs over the course of each subinterval and using that as the height of each rectangle. Okay, so what do we do? Well, we'll go ahead and get my approximation then. I know this Riemann approximation using 4 rectangles, right, will be given by the width of each rectangle is delta x times, and then the height of the first rectangle is going to be given by f of, and in this case, right, the right-hand side is going to be not x equals 1, but x equals 1.5, right? So f of 1.5 will be the height of my first rectangle, plus f of the second rectangle comes at x equals 2, plus f of this third rectangle height is gained by considering the function value at x equals 2.5. And my last rectangle's height is given by the value of my function at x equals 3. All right, so I'm going to go ahead and now go to my calculator and do this all in one fell swoop. So, pardon me, in my calculator, I'm going to go ahead and clear out that sweet exponential regression and toggle off my plot 1. And then our new function, y equals e to the x over 2 plus 2. Great, and it looks like we went 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So about whoa, where did I hit?
You write x down.
Y minus 9.
Goodness. I So we want a -1 to maybe 9. And we want our x scales to be 1. There we go. Thank you. Sorry about that. Goodness. Pretty close. I'm going to go home screen it, and I'm going to utilize that function, my function y1, and just plug in my x value so I don't have to record and can just do one entry and not have to copy down a whole bunch of decimals. And so worry about rounding all the way throughout. So on my home screen, I'm going to go ahead and do delta x is 1/2 times parentheses. I want the value of my function at x equals 1.5 to be the height of my first rectangle. So I'll go ahead and do vars, y vars, function y1 of 1.5. Close, plus vars, y vars, function y1 of, what's my second x value? Oh, 2. And this way I don't have to copy down decimal all the time, I can do a single entry. Plus, my third rectangle height is given by vars, y vars, function y1, and x equals 2.5. And I think this is a great way to avoid copy errors, right, when you're copying down those decimals and plugging them back in. So one more, the rightmost rectangle is given by the value of the function y1 at x equal, what are we going to do here? We're going to go like that, and we're going to do this, and we need 3. Did we get them all now? Mm-hmm. Awesome. Close height. And now I'm getting about 10.404 if we did 3 places. And so raise your hand if you got 10.404. Everybody else get that approximation? Hey, that means we did the same way. So good. We're getting the approximation, right? The approximation for the area underneath the curve. Now, we saw in our activity last class that if you used more and more rectangles, you get a better and better approximation for the exact area underneath the curve. And in our Riemann summary, we'll see that leads to the definition of the definite integral. So a definite integral is going to be the exact area underneath the curve, and that was our final summary, our closure question from last class. All right, so I'm just going to go ahead and do College Board style. We'll say 10.404 square units. We want to keep 3 places in accordance with our calculator allowed AP exam directions. What questions do you guys have about the first part? Okay, then a blast from the past. Let's go ahead and write an equation of a tangent line algebraically to the curve at a given point. So what do we need? Well, we need the same 3 things. We need our x-coordinate of the point of tangency, our y-coordinate of the point of tangency, and our slope of the tangent line. So where do we go to get those things? Well, typically we're given the x-coordinate of the point of tangency, x equals 2. In order to get the y coordinate of the point of tangency, we can evaluate our original y at x equals 2, and so it looks like we get y equals e to the 2 over 2 is 1, and then plus 2 is e plus 2. So are we getting a y coordinate of e plus 2? Is that right? Awesome. And now the only thing that we need is the slope of the tangent line. So many of you on your test correctly calculated the first derivative y prime, right, when asked to write an equation of the tangent line. However, some people didn't evaluate that expression y prime then at my point of tangency in order to generate the slope of the tangent line. So we want to make sure that not only are you calculating y prime, the place you go to find the slope of the curve anywhere along it, but you're actually evaluating the slope of the curve at the x-coordinate of concern. So let's go ahead and generate our y prime. Thank goodness we memorized our words. The derivative of an exponential function is the exponential itself. So e to the x over 2 times the derivative of the exponent, that would be 1/2, times the natural log of the base. An exponential with base e, the natural log of base e is 1, and so then the derivative of plus 2 is 0. So it looks to me like my y prime expression is given by 1/2 e to the x over 2. Is this the slope of the tangent line? Well, this is a generalized expression that gives the slope of the tangent line at any place along the curve. In order to get the slope of the tangent to the curve at x equals 2, I need to evaluate this when x equals 2. So we need to evaluate that y prime expression when x equals 2. So let's do that. So 1/2 e to the, and when x equals 2, I get e to the 2 over 2 is 1. So I'm getting the slope of the tangent is e over 2. Raise your hand if you generated that slope. E over 2 is the slope of my tangent line. Awesome, you guys. We've got all 3 things. That is the x-coordinate of the point of tangency, the y-coordinate of the point of tangency, and the slope of the tangent line. Now ain't nothing to it but to do it. Let's go right to our y minus y sub 1 equals m times the quantity x minus x sub 1. And we'll rewrite y minus e plus 2 equals m, that is e over 2, times quantity x minus 2. Goodness gracious. That's a veritable whirlwind of exponential e's floating around. Let's see if we can make that look a little bit better. So if I want to enter this in my graphing calculator, I would need to solve for y, so I'm going to leave this over here. I'm also going to leave that over here, and I'm going to do this. What if I just add over that e plus 2? Then I don't have to worry about my distributing or combining like terms. It doesn't look the prettiest, but it's going to be easy for a quick check. So let's go ahead and go to our graph. And I'm going to add the equation in our y equals menu that we generated algebraically. That is e over 2 times quantity x minus 2 close quantity plus e plus 2. Uh-oh, lag. What do we do? We'll try. Okay, here we go. Moment of truth, handshake, and I think that looks pretty good. If we did an informal trace at x equals 2, the cursor jumps on and it looks like at the point of tangency, but we could, that's not all, we could use the built-in software. What command do we use to get the calculator to draw that tangent? What do we do for that, Brandon?
Second draw.
Second draw, thank you. Tangent, awesome. That's our fifth option. I can't wait for an overwrite here. So I'm going to tell the calculator at x equals 2. Enter, and it should, oh, look at that. So my blue line style is overriding the red. We know that we've generated algebraically the equation of the tangent line. The calculator is done numerically, and they're agreeing. It's giving me decimals. We did it algebraically and exact, right? So we did it algebraically and exact, and it's giving us a decimal approximation. Awesome. What questions do you guys have on the second part, our tangent line? Okay, then before we get started, I want you to know that linearization is just a new name, right? A fancy new name for using tangent lines. Today we're going to use tangent lines to get approximations of curve function values, and that's going to really set up for our antiderivatives by generating the notion of differentials. That's instead of interpreting dy dx as a single quantity, the derivative of y with respect to x, as two separate quantities. The dy is an infinitesimal change in my y value that corresponds to a dx, an infinitesimal change in my x values, and being able to split those apart. So instead of having a single term, dy dx, we're going to be able to split our dy and our dx into two separate terms and use that to generate antiderivatives and antiderivative functions. And so that's super important, and that's really why we look at linearization right now. Okay, let's go ahead and take care of two different things. So firstly, we want to get you credit for your OTL number 3. At this time, if you could kindly take out your OTL number 3, give yourself credit for those you completed out of 4. The one problem from one section and 3 from another, for a total of 4 book problems. Divide, enter. Multiply by 2 and box your infinite campus score nice and big on top, round to the nearest half point. If you need a stapler, please kindly staple multiple pages together so you get credit for the hard work. There was a graph on the back, right, with your rectangle, so if you could staple your half sheet as well, that would be awesome. Make sure your infinite campus score is visible. And there's a stapler on the side activity table and over here on the left. Let's keep the stapler going. Make sure your infinite campus score is box nice and big. A final check that you have the proper heading, and after it's stapled, go ahead and pass from the back to front, please. Front rows, make sure they're facing the same direction. I appreciate your help grading your assignments each and every day. gotta come back to you. We got an early release schedule. We got a 2-hour release schedule we're dealing with today. We're moving and shaking.
Yeah.
Riley, are you good? Riley, are you good? You send yours up? Okay, just a second. Thank you. Thank you. Okay, great. So I want to make sure that you have an opportunity to get full credit on your stamps from last time. And so while I don't have a slide for this, what we want to do is make sure that we're going to do a separate collection for your 5-4 activity. Your 5-4 activity was Riemann Sums activity. So you don't have to include the extra handout, right, stapled together. What I want to do is just get you your stamps. So make sure that your name is on top of your 5-4 activity. We'll do a separate homework collection for this. It's not homework, but we'll do a separate collection so that I can go through and not take class time to do it, because we're already running short with our 2-hour release. So go ahead and make sure your name's on your 5-4 activity and pass it up, please. You don't have to include your extra handout. List your 5-4 activity, please. And your name. Let's look at your name.
Yeah. No, I thought I almost said you.
Very good with your 5-4 activity? Thank you. Thank you. Okay. Golly gosh. All right. So ladies and gentlemen, I wanted to make sure, last time you did have the full class period, and so we're not going to spend much time on this. I just want to point out that the directions indicate where you're going to look to find the height of a given rectangle. So you guys just need to check this out. If we're dealing with r sub 6, right, on a given interval using left-hand sums, this left-hand sum is telling where you're going to look on each subinterval to gain the height of a particular rectangle. And so once again, we can determine my delta x value by considering the length of the entire interval divided into n equal with rectangles. And so my b minus a all over n can be used to calculate the width of each subinterval. So for us, if we're doing 14 minus 2, it looks like my interval is 12 units long, divided into 6 equally sized rectangles, divided into 6 rectangles, is going to do our 2 units for each one. So once again, I'm not going to do all of these, but I just want to make sure that you're comfortable determining where you're going to use, what function value you're going to use for the height of each individual rectangle. So for r sub 6 using left-hand sums, starting at 2, where am I going to go to get the height of the rectangle on this first subinterval? I'm going to go to the left-hand side. And so this is a case where I'd always be looking at the left-hand side in order to get the height of each rectangle. And so I'm always looking at the left-hand side here. Okay. That's different than if we're doing right-hand function values. Then each subinterval, right? Each subinterval, we're looking at the right-hand side of it to determine the height of a particular rectangle. So I'm going to do this with a different color. In my first interval here, from 2 to 4, I'd look over here to get the height of a particular function value. I'd look over here to get the height of that rectangle, and so on and so forth. Okay, what if we're doing m sub 6? M sub 6, so what do you suppose that m stands for? Nikki? Midpoint, good, thank you. So on each subinterval now, we partition our interval, right? We're going to be looking in the middle of each subinterval, and then going straight up and using the function value produced at the midpoint of each subinterval. And so instead of using 2 or 4, the right or left-hand side of my subinterval to generate the height of a particular rectangle, we'd be using the middle function value. So we'd have to go straight up to the curve and then use that as the height of the given rectangle. We'd be using x equals 5 and going up to the middle and using that function value. X equals 7. X equals 9. Whatever function value is produced there is going to generate the height of the rectangle in that subinterval, and so on and so forth. Everything was going really well until that last one, huh? I don't know if I can handle that. We want PDF. We strive for PDFable in this class, so I think I'm going to have to erase that. That's too hard, no? Okay. So lower estimate uses the least function value. That's not the left-hand side. That's not the right-hand side. That's always gained by looking at the least function value attained over each subinterval. And so, depending upon the shape of your curve, it could be the right-hand side. Right? It could be the right-hand side. But it could be in the middle, right? It could be somewhere in the middle. Or part of the way through a subinterval. We're using the least most function value attained over each subinterval. And one to go, you guys, and that is the upper estimate. The upper estimate always uses the greatest function value achieved over any subinterval to generate the height of the rectangle. That might be the left, it might be the right. In this case, it's the left-hand side. In this case, it's the left-hand side. But in this case, it's the right-hand side. They are going to the greatest function value achieved over each subinterval, and that will determine the height of a rectangle on that corresponding subinterval. Here we're using, look at that, part of the way through the interval. That's when the greatest function value is achieved. Guess what? That's the function value that determines the height of the rectangle for that subinterval. Sweet house. Okay. And I won't finish those in again in the interest of time. What questions do you guys have about generating the correct height? All right, let's put it all together for our Riemann Sum-mary. In the Riemann sum, R sub n equals the sum from 1 to n of f of c sub k times delta x sub k. Each of these parts, right, has a different meaning. So what does n represent? Well, that's the same n from our Bellwork. So what does n refer to, right? Brandon?
N represents the number of subintervals?
Absolutely. So the number of rectangles, for Riemann sums, we're using rectangles, and that's how that R. So the number of subintervals or the number of rectangles. Absolutely. What does the sigma tells us? Well, just like it did last year, the sigma means that we're going to be summing things up. And so we're going to be summing things, adding things up. What does our f of c sub k times delta x sub k represent? Well, that product is representative of the area of a typical rectangle. So that's the area base times height. That's the area of one rectangle. What does the f of c sub k represent? The f of c sub k then would be the height of one rectangle. So that would be the height of a rectangle. And since it says height of one area of one rectangle, I'm going to go ahead and do the height of that rectangle versus the width of that rectangle. The delta x sub k is going to be the width of that rectangle. And the limit then is delta x shrinks towards 0, right? Delta x in this problem represents the width of each rectangle. If that width, delta x, shrinks towards 0, what's happening to the number of rectangles? What's happening to the number of rectangles as their widths shrink towards 0? What's happening to the number of rectangles then? Jake?
There's more.
More and more rectangles, which then do a better and better job of filling up that space, that irregular shaped region underneath the curve. And then we're not such jagged edges there with our rectangles, right? Overcounting or undercounting. In fact, we'll be left with then the exact area underneath the curve. So this would leave us with the exact area underneath the curve. Not just an approximation. Awesome. Okay, so that's what we were to get out of our 5-4 Riemann sum activity. And that leads us to, bless you, the definition of a definite integral. And so the limit as delta x shrinks to 0, right, is the same as the limit as n goes to infinity. So as n goes to infinity, the number of rectangles continue to grow, right, and grow until we fill up that space exactly. That's the definition of the definite integral. So the integral from a to b of f of x with respect to x is called a definite integral. This is the definite integral. As delta x shrinks to 0, n goes to infinity. The number of rectangles grows, as Jake told us. In this case, a represents the left endpoint of my interval. So a represents the left endpoint of my interval. B then represents the right endpoint of my interval. F of x dx, right? That's still representative of the area of a single rectangle. It's just that my rectangle is infinitely thin. So this f of x dx now is the infinitesimal analog of the area of each typical rectangle in my regular Riemann sum definition. This is now the area of one infinitely thin rectangle, right? One infinitely thin rectangle, and so this still represents the area of one rectangle. Whose height is given by f of x, the value of the function, right? The value of the function. So this is still the height of that rectangle. Little guys down. And the dx is my infinitely thin width of that one rectangle. But now our delta x width has shrunk to 0, right? Has shrunk to 0. So now we're summing up an infinite number of function values times widths with respect to x in order to get the exact area underneath the curve. And now this will handle any irregular shaped region. Okay, so this will handle any irregular shaped region, and that's the definition of a definite integral. Awesome. Soon we'll learn how to calculate that. All right, let's do one more approximation with midpoints because midpoints shown up. I added this actually because midpoints showed up then on the free response portion, right? And we had done a lot with left-hand sums and right-hand sums a couple of years ago. I want to make sure that we're comfortable with handling midpoints as well. And Paige, this is why I was thinking that after I added this. And so we're going to go ahead and do R4. Remember, R represents just Riemann sum. We're going to do a Riemann sum means use rectangles. But now we're going to use midpoints as a means for calculating the height of each rectangle on each subinterval. So we'll always start out with our number of rectangles and get delta x. This is saying estimate what is this? 2, 4 f of x dx. This is the definite integral of f of x with respect to x on the interval 2 to 4. And so this is the exact area underneath the curve, right? F of x in between x equals 2 and x equals 4. So there's irregular shaped regions. It looks kind of like the nose cone, right, on a airplane or a jet plane, right? Or this looks like a nose cone on a rocket. Right? That irregular shaped region can be approximated using Riemann sums. In this case, we're going to use midpoints to get that. So let's partition our interval into 4 equal subintervals. Generate our delta x width of each rectangle by doing b minus a all over n. For us, that's 4 minus 2 all over 4. So is that 1/2 again? That 1/2 again? Yep. So we'll go ahead and do 1, 2, 3, 4. We're going to do solid, huh? And we're going to get the height of each rectangle by getting the midpoint. So we need to go in the middle of each subinterval and then go up and function value. There we go. Okay, so I think I want to use my calculator again, right? Since we have negative 5x squared plus 30x minus 37, I think I want to use my calculator to generate that expression. And so it looks to me like we need m sub 4 is given by delta x times first rectangle height. Right, first rectangle height, we'll begin looking at the middle of that first subinterval. That first subinterval spans from x equals 1 to x equals, no, I'm sorry, x equals 2 to x equals, what's that, 2.5? So the function height will begin at looking at x equals what? 2.25. So f of 2.25 will be the height for that first rectangle. Plus f of, and we're not going to use 2.5, we're going to use the midpoint of this next subinterval, 2.5 to 3, so that's going to be 2.75. Is that what you guys are getting? Plus f of 3.25 plus f of 3.75. Are those the midpoints of each subinterval? Awesome. Let's go ahead and do our home screen then for that. In my y equals menu, I can clear out that exponential business. And we'll enter our new function, negative 5x squared plus 30x minus 37. That will allow me on my home screen to do my delta x 1/2 times quantity, bars, y1, 2.25. Y. Okay, let's see how many decimals I messed up there, in parentheses I messed up. So what I'm going to do is throw a little salt over my shoulder and see if anybody else got 12.875. And that's nice, that's nice. That's good news. Okay, a lot of parentheses to keep track of. So it appears as though an approximation for the area underneath the curve in between 2 and 4 is about 12.875. That's already places, and that's using midpoints. We could have used right-hand sums. We could have used left-hand sums, right? We could use upper. We could use lower. It's just a different way of getting a function height. According to the directions, you have to be able to handle, right, which function value on each subinterval will be used to generate the height of that rectangle for Riemann sums. Awesome. Okay. What questions do you guys have about our Riemann summary? Our Riemann summary. Then we've got when approximating the area under a curve on A to B using n rectangles or trapezoids, how do you calculate delta x, right? How do you calculate delta x? Go ahead and write that down with your partner. For each of these three things, we want a true or false. And so each of these are three separate things on the bottom. Please decide with your partner whether that will be true or false. True or false, the lower estimate always uses left-hand sums. True or false, as n approaches infinity, delta x approaches 0. True or false, as n approaches infinity, it doesn't matter whether you use rectangles or trapezoids. Go ahead and decide with your partner the response to each of these four parts. And then we'll conclude our Riemann summary.
E minus A over N. True and false.
Okay, ladies and gentlemen, enough talk, now we eat. Let's go ahead and share your response, please. So, when approximating the area under a curve on A to B using n rectangular trapezoids, how do you calculate delta x? So what formula can we use to calculate delta x? Allie?
B minus A over N.
Delta x equals b minus a all over n. Raise your hand if you have b minus a all over n. That's correct. Thank you. The lower estimate always uses left-hand sums. What do you guys have for that? Go ahead and share with the class. Savannah and Quinn?
False.
False. The lower estimate just uses the least function value in each subinterval to determine the height of the rectangle, right? It doesn't have to be the left-hand side. It could be the right-hand side, depending upon the shape of my curve. Thank you. Raise your hand if you have false for the first one. False for the first one, great. As n goes to infinity, that is the number of rectangles approaches infinity, delta x shrinks towards 0. Is that true or false? Riley?
True.
That's true. Raise your hand if you have true for the second one. That's correct. And the last one, as n goes to infinity, it doesn't matter whether you're using rectangles or trapezoids. What do you guys think about that? Nikki and Evie? Raise your hand if you have true for the last one. True? That's absolutely right. If you're letting your number of shapes, rectangles or trapezoids, go to infinity with delta x shrinking towards 0, you're going to be filling up that space better and better underneath the irregular shaped curve, and that results in the exact area. Whether you started off with a rectangle or a trapezoid, if you let the number of shapes go to infinity, you'll fill up the curve exactly and get the exact area in the definite interval. So that's a true. Way to go, you guys. Okay, so I know in the interest of time that we are jumping right into our activity. We may not get to our closure, but I'm going to pause the recording. And if you guys jump into your groups, you can get going on 4, 7C, 9F, and 10C, skip eligible items. Whatever we get through for stamps is what we get through. We'll stamp next time, but you do need to complete it, right? So let's go ahead and get started right away, and I'll pause the recording.